Hello, good afternoon, everybody. My name is Andrei Masarovich. I am a Senior Resident Solution Architect at Databricks. And today I'm going to talk about MLflow Model Serving. I'm assuming everybody here in the session is familiar with MLflow. MLflow is an end-to-end machine learning framework that has been around since June of 2018. It is an open source package built on the similar to the Spark model in the sense that there's an open source version and then there's a managed offering by Databricks. It was initiated by Databricks folks, but like I said, it's open source. There's a lot of non-Databricks contributors out there. So we're not going to be talking about training here. I mean, MLflow handles experiment tracking, model registry, and ultimately serving. We're going to be focusing on the serving component in this discussion. There are essentially two types of serving, as many of you are aware of. One is offline scoring, which is essentially also called batch scoring. Spark is ideally made for this. The other type of scoring is online scoring or real-time scoring, which is essentially you're basically scoring one record at a time with low latency requirements. So in offline scoring, you're typically consuming vast amounts of data. So an example would be customer recommendations for a, let's say, a drugstore or something. We will also then touch upon, besides the standard MLflow Model Server for real-time scoring, we'll also touch upon custom deployments. And then finally, we will look into Databricks real-time model server, which has recently been announced, and there are some exciting new developments in that area. So, as I mentioned before, the two types of scoring or prediction, we can call it. Offline on the left is high throughput, bulk predictions. Spark, Databricks, you basically you have a table, create a data frame, consume it either through direct code or a UDF. And there's within offline scoring, you can break it down into two categories. One is batch prediction, so that's just a classical Spark job. And you can also have a structured streaming prediction, which is uses Spark structured streaming to be consuming a real-time a feed. Then on the other side, the online prediction, as I mentioned, this is low latency. Typically individual predictions. I mean, you can score more than one if you get them, if they're coming in. This is essentially used for web servers, IoT devices, etc. So this is outside of Spark. There's no Spark here involved. MLflow offers a real-time scoring server that comes in various forms. It's either it's essentially a Python Flask server wrapped by G-Unicorn. You can build it as a container, specifically either an Azure ML container or a SageMaker container, and then you build that Docker container and push it over into the cloud, the specific cloud provider. And then finally, last but not least, is Databricks model serving. That is essentially the ability to expose a public endpoint within Databricks, stand up the web server, and avoid the time-consuming and onerous steps sometimes involved in pushing a container out to a given cloud provider. Here we're going to tackle we're going to address some of the vocabulary, the synonyms. So model serving can be thought of as equivalent to model scoring or model prediction, model inference. And model deployment is the process of pushing the model out into the target platform. As I mentioned, the two types of prediction, if we break down the prediction into categories, we have offline or batch prediction. Within that, we have two subcategories, Spark batch, Spark streaming, and then there's online, which is also called real-time scoring. Here's a diagram of what I just, of the categories of scoring here. On the left, we have the centerpiece of MLflow is the MLflow Model Registry. So after you're done training, typically you go through many iterations of training with different hyperparameters. And when you're satisfied there, you take the best model, the one with the best metrics, you push it into the model registry, and there you can have one or more versions of a given model. And in addition, each version is a monotonically increasing integer. And then in addition, you can tag those versions with what we call stages, which is either production or staging stage. So your favorite model would be called production. And then you can access that with a model URI to retrieve it and deploy it to your favorite target environment. So we have up at on the upper right, there's, as we talked about, offline serving. There's two modes, either Spark batch or Spark structured streaming. And then in online serving, it's a much broader category. It's sort of like the Wild West in the sense there's n number of possible target deployments. We start off with MLflow scoring container. So that's a Docker container. It's made for either SageMaker or Azure ML or just a plain Docker container. Then MLflow has a deployment plugin API, so essentially an extension point, so you can implement your own targets. And currently there are 4 deployment targets. There's TorchServe, Redis AI, the Ray framework, and Algorithmia. And then, of course, you can just roll your own custom web server, just write it from scratch if you really want to, if you have particular needs. And below that, I'm going to demonstrate later, a custom TensorFlow serving. So TensorFlow serving is TensorFlow's serving platform, and I will demonstrate how to grab a registered model and deploy it into TensorFlow serving. And then the brave new world out there of edge devices, there's nothing to prevent you from taking a registered model and pushing it out to your favorite, to whatever edge device you have, IoT, mobile, etc. And then the last category is just hardware devices there, if you really want to go that route with Intel, NVIDIA, and so forth. So as we talked about offline scoring, this is Spark's sweet spot. We can take advantage of distributed nature of Spark. If we have millions or billions of inputs to score, it can either be batch or structured streaming. One of the really nice things about MLflow is the ability to create a UDF, user-defined function. This can be either in Python or SQL, and then to parallelize the scoring for frameworks that are not parallel. So scikit-learn, for example, is not a parallel framework. It's a one-node framework, but using a UDF, you can actually parallelize the scoring. So that, in my opinion, is a really cool feature. And MLflow offers a one-line method of retrieving a model and returning UDF with that model. And this is obviously done from the MLflow registry. So here we illustrate the different ways of scoring. At the top, we create a URI. So MLflow has this concept of a model URI. It can either be the scheme there. The first part is in this example, models. So this refers to a registered model. If you wanted to, you could directly access a run with the runs scheme prefix. But that's we're going to be focusing on the registered model. So MLflow has this concept of flavors, which essentially a flavor is the machine learning framework. So it's either scikit-learn, TensorFlow, PyTorch. That's the native one. So in this case, you get, when you call the native flavor load model, you're going to get exactly what you would in scikit-learn. So that's a scikit-learn object you get. Then you can call the native flavors. In addition, every flavor has something called a PyFunc flavor, which is simply a one-method wrapper API. So this allows us to generically call models with the predict function. So in this example, coincidentally, both scikit-learn and PyFunc call the predict method predict. But for example, in Spark ML, the predict method is typically called transform. But with the PyFunc flavor, we don't have to worry about that. And that allows for powerful tooling, building containers, and just scoring in a generic way. Below that, we look at how to retrieve a UDF. So we're taking that single node scikit-learn object, and we create a Spark UDF, user-defined function, and then we can call that on a data frame, and then that's going to basically distribute the scoring across all the workers. And finally, in the last example, we show how you can even do it from SQL. So we simply take the UDF registered under a given name, and then using the SQL mode in Databricks, we can score using SQL syntax. So online scoring, like I mentioned, there's a large variety of options. This is essentially the key point here is we need to do immediate, very low latency scoring, typically in one record at a time with immediate feedback. A very common option is a REST API web server. Like I said, MLflow comes with its own container. You can build your own. There's nothing to prevent you from embedding your scoring in a browser like TensorFlow Lite. And then there are edge devices, mobile phones, sensors, routers, and then hardware accelerators. So it's really up to the specific use case, how you want to deploy this. This is from the famous Martin Fowler's folks team. Basically, he has a nice breakdown of the different real-time serving options. Typically, one way many people do is literally to embed the model in application code. This, of course, introduces coupling. You can run into tech stack issues, compatible libraries. Another very common way is to do it as a web service, as we talked about before. And then the third one is to basically publish this in a registry as data and then retrieve it on need. So the MLflow Model Server is the actual cornerstone of MLflow real-time deployment. So this is essentially a Python Flask server, or in a very rare, unique case, there's a Java Jetty server for something called MLeap. We'll get into this a little bit later. So the web server exposes a very simple API. There's simply one endpoint. It's called invocations. It accepts three types of inputs. One is CSV. There are two JSON formats. They're called Pandas Split or Pandas Records formats. This is part of the Pandas spec. And then just recently announced is the support for TensorFlow inputs. I'm sorry, tensor inputs, which are actually represented as JSON. And the output is simply a list of predictions. So the CLI, MLflow has basically two modes you can work with. One is the command line interface, the CLI. So from your shell, you can invoke many methods. In this case, what we're doing is we're building a server, or you can actually do it through the API. So within your Python code, you could be building a container that has the server. And in the last line, there are links to the MLflow documentation that describes all of this. So the different modes of the MLflow Model Server are local web server. So that this essentially runs on your laptop. And it's a Python Flask server, just comes up. You can then use curl or Python requests to submit predictions. The other one is the SageMaker Docker container. So this is essentially geared toward, obviously, SageMaker. One of the nice things about the SageMaker Docker container is you can run it in local mode. So before pushing it up to SageMaker, you can actually test it and see if it's working fine. So this is great. I actually use this one a lot on my laptop. There's an analogous Azure ML Docker container. There's also a generic Docker container. And then there, of course, as I mentioned before, there are custom deployment plugin targets. This is a really nice feature that was, I think, released last fall. And it's been eagerly adopted by third-party vendors. In this case, TorchServe, Redis AI, Ray, and Algorithmia. In fact, in MLflow 1.12 in November, there was close collaboration with the core PyTorch/TorchServe team. We worked together to develop that plugin. So in terms of diving into the weeds here, a little bit more technical, there are three incarnations of the MLflow Model Server. The standard one is simply a Python Flask server on the left there. So what we do is we grab the model from the model registry. We take the associated conda YAML file, which is part of the ML project concept. So every model has the code, the actual Python code, serialized in the native framework. So for example, for scikit-learn, it would be a pickle file. For TensorFlow, it would be a saved model.pb file. And then in addition, there's a metadata concept called ML project, which amongst its components contains a conda.yaml file, which lists all the packages. So this can be built for you. This is only for non-Spark ML models. So in the middle box here, if you want to deploy a Spark ML model for real-time scoring, things get a little bit more complicated because now we need to have two processes. One is the Flask web server, and then we need a Spark runtime. So you will submit a request to the Python web server, and it'll simply delegate that to the Spark server. This is obviously only for Spark ML models. And as you can imagine, it's not as performant because Spark is essentially not made for real-time scoring. It's essentially more geared toward ETL batch mode. And then on the right-hand side, we lastly have this concept of, it's called MLeap. MLeap is an open source package that translates a Spark ML model into its own format that does not require Spark runtime. So you basically, it only works for Scala or Java, that is the JVM. So it's basically faster. The only catch is that the MLeap commercial support has been, is no longer available. The company that supported MLeap has gone on to other things, and it's a little bit, it's not quite as mature as one would hope. So it's something that buyer beware. Getting even more technical, here's an example of, at the bottom, we have a client submitting a request, putting the content type there. It's an HTTP post, a request, and then we have three choices. You know, if we deployed the Python, standard Python server, then we have in the middle the Spark ML server, and then on the right we have the MLeap runtime. So those are three different ways we could deploy this, and then it returns essentially a prediction. Here's an example of how to launch. This is the simplest way to launch a server. This would launch on your laptop, so we're using the command line interface here to create a server on the given port, in this case 5001. The option model.-URI, as I mentioned before, this specifies in the registry the address of the model. In this case, it's a scikit-learn iris model, and we're grabbing the production version of it. Here's an example how to score with the CSV format. So we're using the standard command called curl. We submit, as I mentioned before, there's simply one endpoint to the server. It's called invocations. We tell it the content type, in this case it's CSV, and then we submit the data that we want scored. In this case, we're submitting 2 records, and then we get the response there, the prediction for those 2 records. This is a similar example using the JSON split-oriented format. This is a standard pandas format where you specify the first line of the input are the column names, and then subsequently you can have 1 or more rows of data, and we get the same response. This is another option here, record-oriented format. This is a slightly more verbose JSON format in the sense that each row specifies the column in addition to the data. So obviously the split-oriented is probably preferred if you have multiple records. And finally, this was just released a few months ago. As I mentioned, there's a new format called tensor input now. So the request will be cast to a standard Python NumPy array, and it's actually, the input is in JSON, and there are two subtypes of formats per TensorFlow documentation. So you can see this at the TensorFlow serving webpage. Here's an example what it would look like if you were submitting a TensorFlow, a tensor input, that is. Quite similar to the JSON input. So here we're going to look at the 2 standard containers, cloud provider containers that MLflow has. There's, as I said, there's essentially 2 Python containers that you can build. One is the standard Python container, which has the model embedded in it, and then there's a Spark ML one. And as I've mentioned before, SageMaker is the most versatile container in the sense that it can run on your laptop, which is a very useful feature. So Flask is, as some of you might be aware, is a very popular Python web server framework. Of course, we wrap it with GUnicorn to allow for scalability and concurrent requests. It contains the serialized model itself, and it's wrapped by PyFunc, so the tooling can work in a generic way. The Spark ML container has 2 processes within it. One is the Flask web server, which delegates the requests to the Spark server. It's a generic open source Spark. There's nothing Databricks specific about that container. So here are just some links on documentation. These are examples in the CLI. You can you first build a container, and then you can either deploy it to SageMaker. So you'd have to first go into SageMaker, create your endpoint, do all the SageMaker specific stuff, or you can just run it, run.-local runs it on your laptop. Here's an example of using the CLI to build. So in the first example, we're building the container and then pushing it out to SageMaker in the sense of we specify the model URI, that's from the registry, and then your image URL. This is something you need to then previously have created this in SageMaker, so it's all SageMaker specific. And the second example is we're actually building that container and then running it on the local machine at port 5051. And as I mentioned, this is a really, really, in my opinion, nice, cool feature, because the whole process of pushing a container out to a cloud provider, as anybody knows, is pretty tedious. There's a lot of manual steps. Things can go wrong. Turnaround time is typically, if you're lucky, 10 minutes. And so it's not really amenable to testing. Every time you make a change, if you want to test it, it requires you to go through. So Azure ML also has a very similar CLI. So this is, you can either deploy this to Azure Kubernetes servers, which is the preferred mode, or Azure container instances. There's links here to both the CLI and the API. So you can either orchestrate this through Python API or the CLI. And there's an example out here, the last link, that will take you to the actual code and show you how to do that. Here's an example of what an Azure ML image build deployment looks like. You specify the model URI pointing to the model, registered model. You, of course, have to have an Azure ML workspace. That's all Azure ML specific stuff. So it's pretty standard stuff. We mentioned MLeap. So MLeap, like I said, is the intent of MLeap is to provide you the ability to take a Spark ML model. So those are the serialized bits in the Spark ML format, and translate it into an MLeap format that can be then deployed without a Spark server runtime. So this is for the ability to have low latency scoring. It's definitely faster than using a Spark server. And as I mentioned before, the company backing MLeap is no longer providing support, and there are issues of stability, errors, bugs, and documentation. So it's basically a buyer beware issue, but it is available. Here's an example. Here's a link to some code that shows you an end-to-end ML pipeline using MLflow. So if you go to that link, you'll see Python examples for each of these typical stages in the ML pipeline here. On the left here, we essentially go through the classical training cycle, tweaking all the hyperparameters, giving different values for each hyperparameter. This can typically be um, hundreds or thousands of different runs. We record each of those runs in the MLflow repository. When we are done, in the second box there, we select the best model that is being defined by your favorite metric. So, for example, RMSE, you'll take the lowest score. Then you take that best run and push that model into the model registry. So now you have using registry features, you have the ability to track governance, auditability, promote it to different stages. Then once we're done with that stage, we then can launch a server container with the production model, either using Azure or SageMaker or our own. And then finally, we have a client submitting HTTP post requests, either in JSON format or CSV. So those want to see hands-on, source code, feel free to go out to that link. There's a really nice feature that just came out last year, which is MLflow now has a standardized plugin API. So you can create plugins, deployment plugins for your favorite target. So in general, MLflow has a concept of plugins. These plugins can be touch upon various features of MLflow. One is, for example, the metadata store. So typically, MLflow has stores its data in two places. One is the metadata. So these are experiments, runs, input parameters to runs, output metrics. This is typically stored in a SQL database. It can be either MySQL, Postgres, SQLite, and there's a plugin for this too. So somebody's written a plugin, for example, for SQL Server. The other type of plugin that we're concerned about here is a deployment plugin. So here, as I have links to the 4 current plugins: TorchServe, Redis AI, and Algorithmia, and RayServe. Here are examples of these plugin examples, how to deploy them. So we're simply using the MLflow CLI deployment command, we create. So here we have in the first example, obviously it's TorchServe, and we give it a deployment name. There's the -m is, of course, the standard URI to the model in the model registry. And then we have custom provider-specific configuration files. And then for Redis AI, it's a similar thing. Here we give it, the name is going to be the Redis key under which this model is stored, where the endpoint will be, that is, I'm sorry. And then the -m is of course, the model URI. Ray, similar with Ray. Ray is a really cool new feature, supported by a new startup called Anyscale, that's geared toward, in this case, a hyperparameter tuning. And we have, in this case, the configuration is specifying the number of replicas in your cluster. And then there's finally, last but not least, Algorithmia. So if you have an Algorithmia deployment, you can actually take MLflow registered models and deploy them there. Okay, so here we're going to do a little bit of a deep dive into PyTorch. So last November, with MLflow 1.12.0, the Databricks team, or the MLflow team, which had very close collaboration with the core PyTorch folks and integrated essentially PyTorch Lightning, Torch script with Torch serve. So for those of you who are familiar with the PyTorch ecosystem, PyTorch Lightning is essentially a higher level interface over raw PyTorch code. It's sort of analogous in the TensorFlow world of what Keras is to TensorFlow. There is now a format, a serialized format called Torch script, which essentially translates your PyTorch code into a generic Python-free optimized format. So you can actually be scoring this outside of Python. And finally, there's Torch serve, which is PyTorch's analog to TensorFlow serving. So this is a serving framework for Torch script models. And MLflow now has a deep integration with that using the deployment plugin, as we mentioned before. So this is actually really, really exciting, in my opinion, because PyTorch is a increasingly popular deep learning framework. It's getting a lot of traction. And now we have native integration with MLflow. So there's a lot of exciting things that are coming down the road regarding this. Here's a diagram from the PyTorch website. Essentially, you have your data scientist, you have the standard training routine, you're building your PyTorch model, you go through a large number of distributed training. You then generate a optimized model. This is the Torch script, the quote unquote Python free serialized bits. You then register that in the model registry. In this example, we're doing this with the MLflow autolog concept. So MLflow, when you're doing training, there are two modes. You can, in the classical way, before autologging came around, you have to put explicit calls in your code, API calls to the MLflow API, that is simply log metrics. So a log parameter, let's say, so you log all your input parameters explicitly, then you log your metrics, and then you finally log the actual serialized model. So those are all manual steps that you need to obviously execute on your own. And now there's this new feature, or it's been around for a while, but it's been enhanced. It's called autologging. So essentially, once you turn the autolog switch on, there's no MLflow calls at all. In fact, you don't even have to import MLflow in your code. It'll automatically introspect. We have, for a given number of frameworks, which is constantly expanding, we have actually tweaked the code, introspecting into the actual training ML framework code, for example, for scikit-learn, using what's it called? Patching, monkey patching Gorilla. We actually trap the calls for the parameters, and we automatically will take all the input parameters to that given framework, log them for you. So you don't have to explicitly log anything. This is actually pretty cool, wicked cool. Then once it's in the registry, we then access the MLflow Torch serve plugin, and then we finally push it out to the Torch serve framework, deployment framework, wherever that lives, be it in a cloud provider, etc. And then we can do inference on that, using standard Torch serve functionality and APIs. Here's some resources on the TorchServe, on TorchServe and PyTorch. There was a blog post from Databricks. There was also a blog post from the PyTorch team, and there's some third-party articles out there, Medium, and of course there's the source of truth is always on GitHub in the source code. Here's an example. Here are some resources on the Redis AI. So Redis AI, for those of you who are not aware of it, is a NoSQL in-memory database that has been around for a long time. It's extremely powerful, and they have recently expanded into the AI space. So there's a new feature called Redis AI. So they provide you with very, very low latency, quick access, in-memory access to data, models, etc. And they have actually implemented their own deployment plugin for MLflow. So here are some resources, articles, a video. This is actually, I've worked with Redis in the past, and I'm really really impressed and excited about it. So this is a great step forward for both MLflow and Redis AI. As I mentioned before, Ray Serve is it's an open source project that's supported by a company called Anyscale that is focusing on distributed hyperparameter tuning for models. They have also recently, I think beginning of this year, developed a plugin. There's a Databricks blog post with the Ray folks, and then here's a Ray blog, and you can look at the source code and Ray documentations on how to use this. And we demonstrated earlier in the slide the actual MLflow CLI commands, how to deploy this. And then there's Algorithmia, which also has created its own plugin. Here's a bunch of different articles and videos on Algorithmia. So here I'm going to sort of take a segue here and show you how you could actually make completely, let's say you don't have a MLflow deployment plugin yet, or you're not interested in it. You want to make a custom deployment. So what we're going to be doing is essentially building a standard TensorFlow serving Docker container and pulling it from the model registry. So I did this as sort of a side project just to push the envelope on MLflow to see how we could integrate with TensorFlow serving. So as some of you might be aware of, Keras, which is a high-level interface over TensorFlow, has actually been merged into the TensorFlow main branch. So right now, Keras and TensorFlow are essentially married. Before, Keras had a concept of different underlying providers, and now it is essentially a part of the TensorFlow package. Previously, it supported, Keras was standardized on something called HD5. I'm not going to get into the details of that. That's sort of a old legacy format. It's basically a file system in a file. It was the default in Keras TensorFlow 1. It is no longer, it was originally in MLflow the default. It no longer is. So we're not going to dive into that. If you have legacy issues, they can be, we can cover that later. The current TensorFlow format is called saved model, which is a native TensorFlow serialized model format, which also known sometimes as .pb. That is now the default in TensorFlow 2x, which is the current version of the merged Keras TensorFlow offering. And it is, as of MLflow 1.15, it is also the default. So here's an example. We can just focus on the current diagram here. This is just for informational purposes for folks, because we're in transition here. If folks have previous HD5 legacy use case, you can look at the right there. There is a step that will translate an HD5 format into saved model. But if you're starting from scratch, or you can just skip that step, and you will essentially get the saved model by default. And in this example, if you go to the previous link, this is not only just the TensorFlow serving that I demonstrate here. I also demonstrate other TensorFlow serving options, mainly being TensorFlow Lite model, which is made for edge devices, mobile. And then there's TensorFlow.js, which is a format for browsers, JavaScript, JS. So you can embed your scoring inside a browser or on edge devices. So those are two different formats that TensorFlow offers. Now, those are not native, they're not built into MLflow per se, but they can be integrated. MLflow has this concept of artifacts, as I mentioned before. So artifacts are essentially used to store your serialized bits. They are essentially cloud storage based, or any arbitrary object you want. So it could be a PNG, a plot, data, anything you want. So your models are stored under a managed concept called a model artifact. That's the native flavor. So that will be, in this case, saved model. And then in addition, if you have other artifacts you want stored, since MLflow doesn't come with native support for TensorFlow Lite or TensorFlow JS, we can actually store those simply as those bits. So we take the TensorFlow code that serializes that model to a Lite model format or a JS model format, stored as an arbitrary artifact, and then we can later retrieve that for scoring. So that demonstrates the power of MLflow to be extensible. So here's an example of TensorFlow serving example. So this is based upon the standard TensorFlow serving documentation here. We're simply spinning up a TensorFlow serving Docker container. We have, the code has already pulled a registered model from the model registry, and it has used the TensorFlow API, the TensorFlow serving API to embed that saved model format into TensorFlow. So essentially we extract it from MLflow, go through the steps, the standard TensorFlow serving steps, and we build a container, and then we submit a request in TensorFlow JSON syntax, which is slightly different MLflow syntax, but it's essentially the same creature, and we get a prediction there. Here's an example inside MLflow. So here's for those of you who are familiar with MLflow run, every run has, besides the metadata, which, like I mentioned before, is stored in a SQL database, the other part is stored in cloud storage that called the artifacts. So in this case, we have a pretty fancy example here. We have at the top, we have what's called Onyx. So I'll get into that a little bit later, but Onyx is a basically an interoperable model format that is supported by a large number of vendors, principally Microsoft, SageMaker, Facebook, etc., NVIDIA, Intel. Its goal is to have a generic common model format. So as you're well aware of, every framework has its own proprietary or custom model format. And it's very difficult or time consuming, to translate this to another format. So let's say you train in TensorFlow, and for some reason you want to do your scoring in Python, in TorchServe. There's no really easy way to do that. And Onyx has basically tries to, solve this problem by translating that TensorFlow format into a generic Onyx format. And then there's an Onyx runtime that will execute that. And then below the Onyx model, we have a custom artifact, like I mentioned. Onyx is an MLflow concept, so you can save an Onyx model as a managed MLflow model. The TensorFlow JS model artifact below that, with its sub-artifacts, is a custom artifact, so it's not supported by MLflow, so you have to use a native TensorFlow JS command to save that. Same with the TensorFlow Lite model. That's a custom artifact there. The TensorFlow model artifact is actually a managed MLflow artifact. So you can see that by the sub artifact for Onyx model. You'll see ML model. You'll also see it under TensorFlow model. There's an artifact called ML model and the conda YAML. So those are two metadata concepts. The ML model defines metadata around that model, and then the conda.yaml defines the dependencies. And obviously those don't exist for custom artifacts. So yeah, so like if you look at the right-hand box there, you'll see more details in terms of the differences between managed models and unmanaged models. And of course, the managed models, they all leverage the Python concept, which is a generic wrapper with one method called predict that allows all this magical tooling to happen for you. And then there are links there for those examples on GitHub. So as I touched upon Onyx here, it's interoperable model format that has a lot of the heavyweight vendors out there are supporting it. Its theory is train once, deploy anywhere. The caveat here is that it depends upon the actual converters for each one of these frameworks. So if you imagine you have, let's say, 20 frameworks, input frameworks, and you have 20 output frameworks, somebody needs to create actually a converter, from TensorFlow into Onyx format. And so these all vary by maturity. So this is essentially an open source project. In my experience, I've had the best luck with, for example, scikit-learn and TensorFlow. And it really depends upon the interest, customer demand, and so forth. Microsoft is a huge supporter of this. According to their documentation, the Bing search engine, amongst many of the other products, is a heavy user of this. So it's definitely got a lot of traction. And Onyx flavor is a native MLflow model here. So you can treat that. You would essentially have to take your, let's say, your TensorFlow model, call the standard Onyx converter, and then save that in MLflow as a native flavor. And it's also embedded, you can also run Onyx models from the MLflow Model Server. So that's definitely an option there for those who are interested in that. Okay, now we're going to touch upon Databricks. So Databricks, as I mentioned, has a managed MLflow offering, which is essentially brings enterprise features to MLflow in terms of integrating it tightly within Databricks notebooks, security, ACLs, permissions, etc. So here are the four components of MLflow, the four pillars. We have models on the left here, which is essentially the serialized bits, the flavors. So scikit-learn is a flavor, TensorFlow is a flavor, PyTorch is a flavor. Then we have experiment tracking. This is your training cycle. So you're basically going through your hyperparameter loops, and we essentially record the input parameters, the output metrics, any artifacts, the serialized bits of the model, and any arbitrary artifacts you have. And then once you're done with your training, you take the best model, you push it into the registry. And we have a new feature called model serving, which is tightly integrated into Databricks. So you don't have to go, as I mentioned before, if you want to push your model out to a third-party cloud provider, there's a lot of manual steps that are outside of Databricks. So many customers have requested for a much more simple integrated solution. So Databricks now has an offering. It is not currently meant for production. It is, you can call it lightweight, and it is increasingly popular. And Databricks has on its roadmap actually a production grade model serving, which will handle scale and low latency SLAs. So essentially we have one endpoint, an HTTP endpoint that is publicly exposed using standard Databricks authentication, your personal token. Right now, as I mentioned, it's basically in public preview. It's an experimental mode. There's only one node. It's a one node cluster. You can select your instance type, so you have a choice of your instance type, and it's meant for light loads and testing. So let's say you eventually want to run this at scale on your cloud provider, but you're going through iterations, a testing iteration, so you can actually test this all within Databricks. And this model server actually will contain all the versions of your model. So in a sense, it has a multi-model concept, not different models, but different versions of the same model. There's a nice feature you can score directly from the UI for convenience, or of course, using standard HTTP protocol. As I mentioned on the roadmap, this is very exciting. There's a major undertaking to provide production grade serving. So this will be a multi-node cluster with auto scaling, model monitoring, model drift and metrics. You'll be able to access the input requests and the responses if you want to do custom model monitoring, low latency, high availability, scalability, all the fun stuff that Databricks offers. And in addition, there will be GPU support. So here's an example. If you go to the registry, you'll go to the serving tab, and you will basically be able to choose. You can choose your instance type. That is, you launch the model. You can see the different versions, and of course, you can then track it through the model events. Here's an example of what the UI scoring is. There's two actual endpoints here. One is the raw version. So this is version 7, as you can see under the model URL widget here. And in addition, this version has been tagged as a production stage. So you can invoke either one of those. The input, like we mentioned before, is the pandas JSON format. So that on the left there, you can actually just cut and paste a request and then the response is on the right there. Here's an example how you do that. You would do that with curl. You would simply take that endpoint URI, specify the appropriate JSON, and then give it the data. This is exactly the same syntax we saw before. This is the actual MLflow scoring server under the hoods. So it's the exact same format. It's just a different incarnation of it. Here's some resources on Databricks model serving. There's been several blog posts on it. There's official documentation out there in Databricks. So you can actually go and get some more information. Feedback is very important to us. So if you have any questions or comments on this presentation, please feel free to reach out and get in touch with us. And we'll be looking forward to your feedback. Okay, that's basically it. Have a good day and have fun with model serving. Thanks.